Hello, everybody. Dave D Hill here, and I'm with my dad. Say hello, Dad.
Hello,
Dad.
Dad.
You'll get that. So we're here to report what we did today on the book, and I did absolutely nothing at all because I worked on my video last night and this morning because I haven't put out a video for my dissident uh, YouTube channel for a long time. So we had me working on the video and me working on editing and recording last night and this morning, and I finally got it out. So if you want to check it out, you can. YouTube.dissidentscience.com. It's got over 200 views already, so people are remembering me and they go, "Oh, where'd you go for 4 months?" Well, moving. As you can see, we're in a different place. I moved 4 times, and then I want to explain that. And then we are writing this book, so that was one of the reasons. So I plan to get back to it, but today I had to do that since I'm on my vacation. Really, I'm writing on my vacation, and tomorrow I'm going to get back onto the battery, which I started, and I need to put the magnetic loop in there to say, that's how things get started. So that's what I didn't do. I didn't do anything, but I did do it. Check it out, dissidentscience.com. You can um, subscribe if you want. And if you don't like that, you can also subscribe to my dad's channel, youtube.particle.guru will get you to the YouTube channel. That's just a shortcut to get you there, and you can subscribe. People are more subscribing to my dad, and of course when the book comes out, it's going to go nuts. I mean, we'll have throngs of people. We won't know what to do, I'm sure. Right?
They're going to put burning crosses in our front yard.
Oh, wow. But yeah. Anyways, we're here. So I did nothing. So my dad is going to tell us what he did because he did something.
Yeah. I. By the way, there's David's video that he put out today is excellent. He has a really great example of a critical thinker who wouldn't say Einstein wrong for years,
That's true.
and
So if you,
David complained about it. But
yeah,
it was I don't remember what year now.
2000 and actually it was 2016. But when you look at the video that I came out today, it's about 13 minutes. Check it out. It's all edited. It's all scripted. It's really nice. And my dad's there in the video talking about special relativity is not needed, and the placard on the podium says CNPS 2016, and his slide says 2015. So if you are confused, it was actually in 2016, even though his slides on the screen during my video says 2015. I didn't want to
And I
correct that.
apologize. It's
Yeah.
right there in front of everybody. It's
It's
recorded.
really brought my entire video channel down. People are just complaining about that mistake that you had. So,
I always make a little mistake here and there. It's something for my viewers to find and say, "Ha ha, I got him." But this is just a different comment. Dave just said to watch particle.guru. And it's not a .com. It's part of
no, it's part dot guru, folks. People
yeah.
ask me about that. No, there's a dot guru. You can get it. It's more expensive. So you can just put it, buy it and cyber squat on something that you think you're an expert at, and you can get, dehilster.guru if you want.
So
So
even though I have like over 120 videos under that YouTube channel, the video which is special relativity is not needed. The paper I wrote is not part of that. The only way you can find it is go to the CNPS website, or you could. Here's one of the things that's easy to do. You Google my name, Bob D. Hilster, and special relativity not
it's
needed.
just special relativity.
Special relativity not needed, and it'll pop up and you can watch it. And just what about last Saturday? I checked the views and there's over 1,800 views on that video alone in what, 4 years?
Yeah, a lot of people are
and
watching
it's
it.
not even being advertised. It's a constant.
People find it.
People, yeah, yeah. So I'm just telling you about it. If you're interested to understand my reason why special relativity is not needed, watch the video.
In fact, if you go to my YouTube channel and watch the video today, I do some things like put the link to his video in my description. So you don't even need to search for it. Just go to YouTube, just.dissonantscience.com, watch my latest video, and you will see a little excerpt where he talks about frustrating me and things like that. But I always put those in the you know,
I've
I'm
done
gonna
that
have to
once.
hire somebody to
I've
go
done
through
that
Dad's
twice.
videos
Twice.
and put stuff in the tags and put stuff in the description so people like, oh, it's really cool. And he puts on the screen some like UTA.be, which is Belgium, / capital F ZXR49 F669WR10 and all the different capitalizations. And he goes, oh, you can watch this video. Now, who's going to type that in? It's got to put them in the description. So please, all of you subscribers for him, please get mad at him. So anyways, I want to say hello to Farouk. Hello, guys. David Nicholas, and he's got, I guess, his channel. Who knows? We've been having, let me, see those. Are those spam? Probably. I don't know, David Nicholas, are you giving us stuff that's real? Or maybe not. I don't know. Anyways, I can't put those on the screen, but I want to say, Jerry Harvey, where to find the video, what keywords to look up. Oh, okay, yeah. So, which you really do have to look up. If you go to my video, I have it actually in the description of the link. So, the description of the video. So, if you go there, you can find it, or you can also find. You have to do say special relativity is not needed. D Hillster. Or I think you can just say, let me see, special, you may be able to do that special,
Yeah,
but you can remember that. Relativity is not needed. Let's see if that comes out. Yep, just do that. Say special relativity is not needed. And the first person that pops up on planet Earth is Bob D. Hillster. So, and it's from July 26, 2016, even though the slides say 2015. So. Oh, it's a link to our YouTube channels. Well, thank you, Dave Nicholas. I'm sorry about that. I just don't know because, because of what we talk about sometimes is sort of controversial. So we get people come in who are trolls. My dad doesn't even know what a troll is. So we want to say hello to Farouk. Thank you for joining us. And if you haven't watched our videos from before, folks, you should check them out. We got some pretty good discussions going on. In fact, after this week, even though we won't be done with the book, but we're going to be making a huge headway into that book. We'll be pretty much on the home stretch after that. We're planning to do some chats. Probably put them, we'll put them on the book here and maybe even stream it to my father's channel as well. But regardless, we plan to do some of these talks together because we're always talking about it. And the other thing too is we're looking to record them and put them on the channel. So, and what I plan to do is every time my dad and I have this really, what am I putting that up there for? Come on, putting the wrong one up there. Here we go. Every time my dad and I decide that I go over to his bedroom or his office, and or he comes over to my office here. We end up talking about really great things, and then we don't record that. And when our book comes out and the model comes out, and we become world famous, and we're the most important people on the planet in science, which, right. Woohoo! Yeah, right. Anyways, I am actually doing that for prosperity or what do they call it?
Posterity.
Posterity.
Or
because just in case.
Posterior.
Just in case. Like this model is something because we have a feeling it could be, then at least we got these recorded and not lost into the ether, although we don't believe it gets lost into the ether because we don't believe ether. We're not etherists, but hey, that's a different story. So Dad, tell us again, thank you everybody. If you have a question for us specifically or comment, that's great. Raymond D Hillster. Hi, Bob D Hillster from hello from the Netherlands. There is one of our relatives. Right there, Raymond D. Hillster. Hi, Bob. Hey, we only found D. Hillsters because of the internet many years ago. So now I know there were other dehilsters. We thought we were the only ones, and we were so unique. And then another Raymond.
Oh,
There's Raymond.
yeah.
What's Raymond doing? He ruined our illusion that we were the only dehilsters on Earth. But we're actually happy. There's
I
probably about
actually found one in South Africa.
yeah, but that was a while back. I don't know if he's there anymore. But Raymond, I do see you, and thank you for tuning in.
Hey, Raymond, are you? There's a Philip D.
Philip
Hilster.
Hilster? That was a while back.
No, his last name isn't D. Hilster, but he's part of our heritage, I think. The guy in South Africa was a descendant of Philip somebody. I got the whole history of that, of our family. And I'm just curious if you're also a descendant in that line.
Okay, we're going to get off this. We're going to talk to you later, Raymond, because we have actually people in questions who is better, Euler or Gauss. Well, we're not going to answer that question today, but I'm not sure if there's any better. But let's talk about what my dad did on the book today, and it's going along quite well, actually.
Yeah, well, I talked about the diode, and I actually finished it up, at least the part that's in the hacking section. I haven't done it yet, but I want to do an actual spreadsheet calculation if I can find the algorithm that I need to apply to the particle model and actually generate an IV curve using the particle model and a spreadsheet, but I have to generate an algorithm. Whether I ever get that done in time for the book is another question. But I've done that for the resistor circuits and for the capacitor and inductor. I've done it for 3 of them, using a spreadsheet to generate what essentially is a voltage current kind of curve, specifically for capacitor and inductor. So I want to do that for the diode and generate that curve. So that's not done. But the explanation of why the curve is the way it is in the hack 3 section of the book. Now, Dave, I'm really concerned a bit here. Because I'm starting to do the same thing for the transistor. Now, the transistor has an interesting point to it that's different than the other ones. But how many of our readers are really going to be really interested in whether you can explain an IV curve or not? I mean,
I think people are, Dad, very much so. Here's the problem. Here's the problem with most models. Most models that people propose tell you all about the atom, the way the atoms are put together. Because some of the most popular models, the models out there of supposedly of everything, start with the atoms. And this is the way atoms are constructed, and which is totally fine, because I think some of those models have some merit, because we don't do that. We tell you how it sort of functions, but we don't tell you, the actual periodic table and why that happens. That's fact 4, which we're not going to do. But these people, they have all their models, but they don't apply it to very much. And there's 2 things that I think that are very important. One is that we give physicality to everything in the universe that people just didn't know about. I think if someone asked me what this book is about, it's like, one sentence. Well, it gives physicality to all those things that no one else has given physicality to, like light and gravity and magnetism and electricity. And because of that means we have a physical model of everything, which we can start explaining things way better than other people, because they're just talking about fields, they're talking about equations, all that kind of stuff. Yeah. So what happens is when a person gets to this book, they're going to go, oh, particles nice, but it doesn't apply to anything. Well, guess what? We have one of the authors of the model is an electrical engineer, and not only that, we're explaining electrical components. Okay, folks, watch this. I'm going to ask my dad this question. You guys are witness to this, all right? Here we go. Dad, are you explaining things in a physical sense that anyone else in the world is talking about, like a transistor or a diode? Are you explaining things that is the actual physics behind it that no other human beings are doing?
As far as I know, the IV curve for a diode, what's really happening and why it works the way it does, why the voltage, you can increase the current, but the voltage still stays at 0.7
Wow,
volts.
it's just
No,
a yes or no question. Let's try it again. Dad,
no,
I don't
no.
remember the question
No,
anymore.
the answer is not no, it's yes. I get it, Dave. I get the question.
Well, you
But
get what? You
the,
get what?
that that I'm explaining something physical that nobody else has explained, and that ought to be interesting, but it isn't going to be interesting to everybody. It's probably only going to be interesting to an electrical engineer.
Well, let me see.
Because
Do,
they're
do,
the
do
only
people
ones that even,
do
even
pe- do people like know or have electronics? And if they people like a model and they find out that we're able to describe, for instance, basically all we're doing is, well, all we're doing all we're doing is giving a model for light and gravity and magnetic fields and electricity. That's all.
I'm talking
But
about the
I mean, because of that, we can do this,
Yeah.
and because you're an electrical engineer, this is fantastic.
Well,
So you
it
don't
is
have to.
It is to
you
me, but
you don't.
I think it may be a customer limited.
Okay,
Most
here's
people, excuse me, let me fill it. Go on. All right. Most people like to see how to use it. What is a diode used for? Not what they.
No, they didn't buy. They're not going to buy our book for that. They're buying the book because they go, you know, someone told me this is the first book since Newton that actually tells me what the heck everything is physically. Oops, you're in front of the microphone.
No,
now.
I do.
But that's what. And so,
Okay.
I think I know what you're saying, but that the whole thing is that the electrical engineering part is very important because it shows to a very high degree how this particle model allows us to see and describe something like all of electronics, what do you have? Holes moving holes?
Hey, I can show you one I put in the book that I'm going to take out. Anyway, that's a concern of mine that
Yeah, you
that
don't.
I spent this one hacking section on a diode to explain the curve, and I'm concerned about whether they're really interested in that. I think it's important. You know that, but now I did the transistor. I started the transistor today, and I said, okay, what's the IV curve for a transistor? If you open the book, we can show the our people here, or not. No, we can't do that.
I don't want to show them the book too much because they're going to buy the book.
Well, this is just a standard IV curve of a transistor, so you can get in the
Well, I can find that anywhere then.
right.
But okay.
Yeah, you can find that anywhere. And anyway, I'm thinking, okay, I need to explain the transistor the same way I did the diode to
Yeah.
explain that curve. And the thing starts out like a diode, but then it goes into saturation. And that's
Now you've just lost everybody on.
I
you
know,
so,
I know. I'm just
so
saying.
so
is,
okay. Let's
all I'm saying is the hacking part's going to explain how that happens, but I haven't done it yet. I did a whole video on the transistor and I never got to that point. All I did was the same thing that everybody else did. It explained the circuit. Instead of using whole current, I used G-flow. That didn't explain the curve. I never did that in the video.
That's okay, Dad. Now, I want to step back a little bit because I mean we're talking very detailed stuff here. We have a question. We're gonna look at the question here.
Okay.
But let's look at a few things. So what happens to electronic components as you put a current through them? They ramp up and start working. And when they start working, well, the current flows and the current gets to a steady state more or less, right?
Yeah.
Most of the time it's not always the case. I think in a capacitor it can
Well, you can get an
Right.
inductor capacitor circuit that'll oscillate,
Right.
even though it's DC.
Right. That's okay. That's okay. But regardless, the electronic components, which today we have zero explanation physically. All we have are equations that we have come up with for electronics, and we're doing pretty darn well with them. Look at what we built. I mean, if you took away electrical engineers from our civilization, we'd be almost nowhere. So the importance of electrical engineering is amazing, and the ability and the knowledge that we have to explain the circuits and the components of the circuits, what's actually physically happening is a big goose egg zero. So what my dad is talking about is trying to use the particle model, which is actually real particles going through real materials, and these materials have simply, here's one, doping. Doping makes less space, right?
Well, sometimes more, sometimes less.
Okay, doping changes the amount of space in the atomic structure, and the G1 particles to go through them. Just imagine like we have a bunch of suns out in the universe, and they're all placed in a way, and I shoot a comet through it. That's the way our model works. So he is now he's taking these components and making spreadsheets with them to say, okay, at this point there's this is happening, this happening, this happening. So then he can graph it. So our particle model should match the graph of how voltage, current, like electricity, goes through a component. So that's what
and the algorithm used in the spreadsheet matches the physics I talk about in how it works. There has to be that match, or it's it's just playing games.
Hey, Fearful Milk, thank you. We will be back, and thanks for coming by. Okay, so we do have a question. So you've been working on the diode, then on the transistor, and then the transistor. You have to pretend this is not here.
I do.
Okay.
I can see right through
because
it.
we have this wide angle thing. This thing is like, it's not that far from me. I mean, I can almost get my hand in between it because wide angle makes everything look a lot further. So when I turn to look at my father, he's got a big microphone in his face, but it works out real well. We got a good mic. Okay, so we're going to put up a question here. This is just a totally different question, Dad, but since people are here and taking the time, we do want to do that. So here's the question, and we can put them up here. Question for you. I've not yet had a chance to watch your videos, so this might be a silly question. Can your theory explain how to populate the structure seen in the universe from nowhere, i.e. Einstein's RIC equals 0? Are you talking about the Big Bang? So David, if you are hopefully still there, are you saying that fill space or the Big Bang? Or what are you talking about? Are you talking about space-time, or not sure? So if you can maybe clarify that question, we'll be able to answer it. But right now, I'm not familiar with Einstein's RIC equals 0. Yeah, we talk about the Big Bang a lot. We talk about how that's a big bust, reasons that isn't a good theory. So anyways, if you could clarify that a little bit, and maybe an explanation, we'll be able to answer that question. So I think he's here. But again, thank you again for coming. So what I plan on doing tomorrow is to continue with the battery, get the battery diagram done. That is how a battery works. And a battery basically, it was pretty interesting. I talked about it yesterday. It's got chemicals in it, so a battery's just sitting there, doesn't do anything. And then when you put a wire and a load on it, then things start happening, and the chemical reactions happen because electrons or G1 particles come into certain molecules, and those molecules do chemical reactions, which then pass the electrical charge through the battery, and they pick up more G1 particles or electrons, and that keeps going around and around and around. When it stops, it sort of stops. But we need to explain those so that when we get to the electrical components, that we can have those explanations for people so that they can sort of understand them. Again, we're using the electrical engineering part because it is such a great, it shows you all the aspects of the model. The model has gravitational fields, which are particles, that's on our website. We can show you that. So if you go to our website, which I'm going to go to now, and then I'll bring that up, and you go underneath particle model, there's a movement classification, which is basically this is really our whole model in a nutshell, basically. So let me get this up here and then be able to share it with you so it's at least big enough. Sharing here, bum, 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 and share. There we go. So if get rid of the banners here so you can see this, hide it. So this is our model in a nutshell. Particles have 4 classifications, and we even I came up with some new words. I think they've been used. Maybe gravitic hasn't been, but because we have electric and magnetic, we didn't have an ick word for light or gravity, so I said gravitic and luminic. They may exist, but that's pretty much what everything that we deal with. And the gravitic is basically particles that go in all directions in straight lines, and that's what causes gravity. So if you are at the level of atoms, you have a nucleon and you have G2 particles, a level down, it's the gravity for that the level G1 level. Then you have the electrons going around the nucleus. That's caused by the G1 gravitic field. Electric fields are simply particles that are all going in the same direction. And my dad, so the gravitic came from Lesage, the magnetic came from Denis, and the aluminic came from my father. That should be switched. Yeah, he came up with that, and that's really what started this whole thing. And I came back and said, okay, well, the electric part is just, particles moving. So I think we use all of these concepts are used, except for really luminic, in the electric circuits. Luminic is really more used for digital.
I explained the light emitting diode, and light emitting diode is going to put out a pattern like that.
Oh boy, duh, Dave. There you go. Dad schooling his son. Way to go, Dave. Yep, that makes sense. So those are the and these four components are you. And if you use electrical engineering, which has never been described before, and you have our particle model being able to describe those things, that's why we're using it, because we're killing a number of birds with one stone. Is that our model needs to be applied to show things that it can do. And of course it can do the double slit experiment with the detector, which no one else can explain. It can explain all kinds of things. It can explain why the Earth's expanding, how you take nucleons and you put G1 particles, and guess what? You make atoms out of them, or you make atoms bigger, etc. So that's why we're using electrical. I'm going to, look at Raymond D Hillster. He's still hanging around. Now I know. Hey, Raymond, another D Hillster. If we become famous and stuff, he wants to, he's going to be D Hillster too.
How
hey,
Raymond, is he?
Raymond, let me tell you, Raymond. I'm sorry, folks. This is the person I'm sure we're related to, because our name's so sort of rare. Hey, Raymond, remember, it could go both ways, right? Welcome to fame or famine. No, fame
or infamy
or famine, really. But anyways, he asked about, you could make luminic photonic. Let me tell you why we're not doing it photonic. Photon, the word, has a loaded connotation. Photons have this connotation that a photon, one particle, can hold the information of a frequency. So you can have one photon that's a blue photon and one photon that's a red photon, right? And that just isn't possible. So the reason we didn't use photonic, which I did think of, is because it's got that connotation. Oh, those are photons. They're not. Okay. So that's a real technical reason, but that's why. Okay, so Dave Nicholas is, I didn't show that. There we go. Raymond D Hillster says, luminic photonic, perhaps. Yeah, it's a good question though, Ray. Very good. He can catch on. Maybe, he'll be one of our ambassadors with the particle model. Or he could go around and say, hey, my famous family over there, I'm a D Hillster too. And of course I've been part of it. So anyways, hope that explains that. Now we have Dave Nicholas, and this is one of the things I like about StreamYard, is we can throw those comments right up there. Yeah, so all the matter had to come from somewhere. All the particles and mass are made up of quarks, up, down, the quarks, and carries from Big Bang. Okay, well, Dave, we do not subscribe to the Big Bang. The reason we don't subscribe to the Big Bang, there's a real reason and an explanation, is why do people say the Big Bang exists? Why? Redshift, right? And maybe what I'll do is I'll have my father talk about um, the redshift, and well, how we explain it. So I will tell you the mainstream, and then I'll turn it over to my father, who's actually talked about this in one of your videos
I
too.
could give
Yeah.
them the name of it. It's
Oh yeah, we'll get to that. Hold on. So the reason people claim that there is a Big Bang is because of redshift. The redshift means, oh, it's like a ambulance. So if you hear an ambulance going by you, or a police car, or a fire truck, neener, 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 you hear it go down. I'm trying to do the European one, not the United States one. Anyways, you hear that, and it's called the Doppler shift. Well, the idea is that if something's moving away from you and it's emitting light, there's a shift in the frequency, so what you see then, of course, it's going to be spread out, and what you hear is a drop in the frequency, and therefore the reason when we look all around in the sky, they claim when you look all around the sky that you see things redshifted. Oh, redshift means it would be moving away. Oh, if everything's moving away, the universe is expanding. Oh, if the universe is expanding, then it had to start from somewhere. If it had to start with somewhere, it's called the Big Bang, which was actually a derogatory name that they used for this idea, but it's stuck now. But there are other explanations. Borkert is a good person to look up. Glenn Borkert. He's an excellent person. George Coyne, who's one of his students, basically talks about consciousness and all that stuff. You like into that, but he talks about the same thing. So we're going to have my father talk about why redshift, what's considered to be redshift, isn't really movement of things. So this is your answer to your question. Before we get to this, is that okay? Oh, good night, Raymond. We'll get to. It's 2 a.m. Boy, what are you doing up there, boy? It's Thursday. Oh, it's Friday there. So anyways, good night, Raymond. Thanks for coming by. But anyways, we did it earlier. Maybe it's going to... Okay. So the whole thing is, to answer your question, Dave, we do not believe that everything started and exploded and started stuff. We believe in an eternal universe. We believe in infinite up and infinite down. There's no ultimate particle, because if there is, it doesn't make sense, because you'd have to create the universe, with a bunch of rules. What does it have? A rule book? Anyways, we believe in infinite space, infinite time, infinitely up structures, and infinitely down, meaning our solar system and all those bigger structures above us, making bigger structures, and down below. So my dad's going to talk about the particle model and why, if you say, oh, redshift isn't moving, why do we see redshift? Take it over, Daddy-O.
Okay.
It's
Thank
like,
you for
shut
the
up,
big
Dave.
introduction.
It's like, shut up, Dave.
And
Let me
I
speak.
made a video, and the title of the video is Redshift and Tired Light.
Redshift and tired light. I'll put that in there.
You go to the particle.guru website, and you'll find that one. And it's, let me just say for a moment, the reason they come up with the final answer that it's moving away is because they make two assumptions. One of them's good. The first assumption is that the light coming from the star is burning hydrogen. And hydrogen gives a spectrum line because of what it's burning. That's the first assumption, and that's probably pretty good. They burn hydrogen in the lab, and they got close stars and further stars and you can see it's pretty consistent, so it's a fair assumption, but you got to have that first. You have to know that you believe that it's burning hydrogen, that distant star. Second thing they assume is that light never changes as it moves through space.
Right.
Doesn't change
right.
when it moves through space. And then you're left with the only conclusion, well, if there is a redshift, it's got to be moving away. Okay. All right, so my opinion is I agree, and I'm not an expert, I'm just reading what I read, and I agree that's hydrogen and there is a shift. But in the particle model, the G2 particle is subject to drag as it goes through space. Now the G2 particle field is made of the G2 particle field. Our assumption in proposing that is that it is so much really faster than light. It has to be if G2 gravity bends light, which is one of the other propositions that we make. Okay, so it has drag, but light is going at speed c. Let's assume for a moment G2 particle field's going at c squared, which is a thing I kind of throw around. Probably not right, but
That's fast.
Because the speed is so different, you get the faster, well, not the faster it goes, but the speed difference determines the percent drag. And since the speed difference is huge, it doesn't get much drag. But what it does one thing. It slows the peaks down as they, let me do it this way. As the light is going by, you have peaks that are spaced, but if they all slow down, it isn't that the wavelength changes or the frequency changes. The wavelength probably stays the same, but when it gets all the way to the Earth and it hits our eye and we're observing it like we're observing this line in the spectral analysis, the peaks, if they go fast, the arrival time is quick. If it's slowed down and moving slow, the arrival time of peaks is less.
So
that's redshift.
Yeah, the G1 particles hit your eye slower than when they started out.
And so that gives you a redshift, and you don't have to have it moving away. Can it be moving away? Of course. I mean, I'm not saying there aren't stars moving away. In fact, there is a very well-known galaxy moving right at us. And guess what? All of the stars in the Andromeda galaxy are blue shifted because they're coming towards us. One of the reasons they know it's moving towards us is it's blue shifted. And it's our closest galaxy. There's another,
well, wait a minute. If it's blue shifted, then the redshift should show the other stuff. So why are we seeing blue shifted? Why is that okay with? So we're saying that blue shift is okay with the standard model sees that, right?
Oh yeah.
And we say that's okay, but then redshift we don't like because we don't like the Big Bang. So they're going to say, see,
if
you're
you
biased.
read between the lines and you pin them down, they'll say there are other blue shifts out there. It isn't, I don't, but, and Andromeda is one classic example because it's so close and you can measure it and even measure it different ways to know it's coming at you. That doesn't matter. All the rest of them, whatever all the rest are redshifted. Therefore, you make the assumption that nothing happens to light as it travels. You come up with expanding universe, at least for those that are moving away. Locally, in any location in the universe, you could have ones coming at you. Just the way the universe is.
So Dave.
But the second point in the video is tired light, and that's based on energy. I believe Zwicky is the name of the scientist who worked on this back in the 1920 area, and he said that what happens is clearly light intensity changes as it comes to you, right? It's weaker and weaker as it comes, so it's losing energy, and if it's losing energy, you can go to the very famous equation E equals h, the Planck's constant times frequency.
Right.
And you can show with that equation if energy drops, frequency drops. When frequency drops, it's a redshift.
So what's H?
Planck's constant.
Yeah, that's right. In our model, what constants do we have in our model?
Well, nothing's absolutely constant, but our gravity equation has at least two.
Right. But constants don't, the universe doesn't know about constants,
but,
really.
But Zwicky said, maybe that's what's causing a redshift, and therefore the stars are not expanding. But the intensity does decrease. If you have a G1 particle field that's coming at this stream of light from a distant star, every once in a while a G1 particle is going to hit a peak, and they're going to knock each other away, and sometime later hit it again, knock each other away.
You're talking about G1 collisions when you just talked about G2 fields. I'm
G2
lost.
fields is for drag. This isn't drag. This is intensity.
Oh, okay, gotcha.
Intensity is when the intensity of that stream of the light that you had up there, the luminic light,
Right.
the cluster at the peak is what really determines the energy of the light.
Sure.
And if you keep knocking them away as they go through, even if this one pinpointed line coming from that star all the way to your telescope, the intensity is reduced. But that has nothing to do with the frequency or wavelength, just the intensity. But Zwicky was saying energy, and I think he related it to the equation energy equals Planck's constant times frequency, and therefore energy goes down, frequency goes down. Therefore, when you lose energy, it's a redshift.
Right.
And that says you don't have to have the stars moving away. Something happens in transition.
Right. Okay, let's take a look at some of the comments here. So we'll put this one up. This was David Dave Nicholas, who asked, he says, I agree, yes, so like traveling through plasma density for EG. So I guess he's talking about plasma, light traveling through,
the corona of the sun is a type of plasma, and the question is that normally, the answer to that is normally when light goes from a one medium to another, depending on the index rating of the medium. Air is 1, and then the rest of it is related to with the index of 1. The standard answer, it slows down. That's not the TPM answer. We have a similar reason for why there's a delay, but not because of slowdown. When that stream of light goes through a prism, the speed is the same, but the path is not straight. It can't possibly go straight.
Right.
So it's a longer path, and if you measure straight line distance, yeah, it appears to slow down through the prism as opposed to through air. But if you look at the speed of the particle going at speed c into the prism, it's just no way. There's no way that I can ever imagine it going in a straight line. It's going to zigzag up, down, sideways, around, crazy path. So the longer path brings the phase of the light out at a later time when you measure straight line versus this crooked line.
Mm-hmm. Right.
So no, the particle model, I'm not of the opinion that it slows down. The particle doesn't slow down. The measurement of the wave by a straight line appears to make a light look like it slows down, but the particle isn't.
It's just taking a longer path.
Taking a longer path.
Okay, so here's a comment or question. It says, what about the one-way speed of light?
Yeah, does light go backwards? Is that what the...
I don't know. I guess you're going to have to clarify what that... Is that a concept, Tommy Bird? We can get back to that. Not sure. I've sort of maybe heard of it, but I don't know about that. I think there's a comment, but I think he also corrected himself. So this is Jerry Harvey. I thought Fritz Zwicky had an idea of tire light since it has been traveling from a much further distance than stars, such more nearby. He says, okay, laugh out loud, sorry. I think he probably got an answer when you were talking. He says, I have a sort of multifaceted question. What alternative views exist that account for some of the established proofs of relativity and other popular theoretical concepts? What alternative views exist that account for some of the established proofs? That's a good question. I can probably answer that for you. Okay, so let's look at the question. What alternative views exist that account for some of the established proofs? Well, of course, you can't prove anything. What you can do is supposedly show that data matches. Let me give you some examples of things that are not proof, but they say they are. The simplest one is from my film. If you haven't seen my film, you can go to it at EinsteinWrong.com. and you can watch the film for $3 or $10. You can buy it and watch it as many times as you want. Why do I charge for it? Because that's the only way we can have it on demand, and the people who invested the money into it, I feel only that's the way it should be done. So it basically pays for itself to be on demand and available for people to watch. Okay, but anyways, if you watch that film, you're going to see in that film the atomic clock experiment. It turns out that Dr. Eberly Spencer, who is a person both of us know from the NPA days, she has a doctoral in mathematics, PhD from MIT, very, very bright woman. And she actually asked the two experimentalists who did that, which basically put an atomic clock on the plane and then rode it around the Earth, one west going one way, one going east. They got monies to do that. And then they concluded by publishing that this showed time dilation, therefore showing that special relativity was correct, and or general relativity, I guess. If long story, I won't get into that one. But regardless, it turns out that they did a very big no-no, which was they sent the raw data to her. Normally, when you are a scientist, in order for you to protect your interpretation, because your interpretation will depend on will be important, because it will say whether you are going to receive your next funds for your next experiment. Because if you're going out to prove Einstein correct and you prove him wrong, everybody's going to laugh at you, because of course everybody knows Einstein's right. So basically what they did is they sent her the raw data. At that time, this was around 2005 and 2006. Both of the gentlemen were in their 80s, their mid 80s or late 80s, so they were old. So they probably just didn't realize that they were doing that no-no, because at that time they sent the raw data, and then she went to plot that data and found out that the way that they had made their data fit general relativity was to start the curve, the experiment, 23 hours before the experiment started. So the curve for the time for the experiment, there were two things. One, there was a gap from when they were on the plane and then I guess on the ground and taking off. There was some type of gap there, and then they filled the gap with a line that just made no sense. It didn't. Any person, she said, with a one of those rulers that you can bend sort of make nice, would make a nice smooth curve. They had some bizarre curve that actually took a weird leap, and that was one problem. The second problem with the data she found was that in order for them to project the right curve, they had to, the experiment had to start 23 hours, the clocks had to start, they had to know they were going on a trip, she said, and basically 23 hours discover some consciousness of the clocks, discovered that they were going on a trip, and all of a sudden they start the experiment without everybody, and the 23 hours before it, even though the experiment started 23 hours after this line started the experiment, that was the only way they could fit the data. So long story short is that data that they say, very common, it's probably the most common answer that we have from alternative views and people who sit down and look at this stuff, is that the data is literally fudged in this case. Or if you go to a particle accelerator in the same film, in my film, you'll find that the particle accelerator, the Dr. Kelsey, I think his name is, or Kelsey? Kelsey. Dr. Kelsey explained to us that he had to unteach, listen to what I'm saying, unteach his grad students about special relativity, because it doesn't work. Why? Because one of the things they should see in particle accelerators, especially particle accelerators, is mass increase. And guess what they don't see? Mass increase. Therefore, relativity is saying there's mass increase. We don't see it. I'm a particle physicist who even subscribes to a lot of the standard model, and I'm saying it ain't there. So the experimentalists and the theoretical physicists, in fact, just a side story that was not in the film, before we filmed that scene, we were sitting down at breakfast, which I paid for to be nice and talk with him, and I pre-interviewed him because you want to get a feel of what things you can ask and what things you not. I said, so what's it like to be theoretical physicist, and he looked up to me as if I had just told him his mom was a bad person, and he said, "Don't ever accuse me of being a theoretical physicist. There's nothing theoretical about physics." And I think that was one of the reasons he agreed to be in my film, which was I figured, no one would want to be in that film. So those are two examples of.
There's another one that I made a video on.
Okay.
That's LIGO. And Jerry may be aware of that. Was only a year ago?
Right, gravitational waves.
Whoa. Yeah, they claimed they had proof of gravitational waves. But in fact, what they had proof of was a phase shift in the interferometers that measured the so-called gravity waves. So they have direct proof of a phase shift, but they don't have direct proof of gravity waves. They're assuming because they like relativity, and they expected that with relativity, this huge cataclysmic explosion that happened out there would generate waves of gravitational waves in time-space, and therefore would do something to the interferometer, and it did. Their explanation was the length of the arms, one of the lengths of the arms of the interferometer changed because of length contraction.
Right.
And that's what caused the phase shift. Sounds very logical, but they only have proof of phase shift, not of the waves. In my video titled, it says, it's got LIGO in the title. No, I think it says TPM, or Particle Guru Explains LIGO. And I use the G2 particle as a possible, maybe reaching a little bit, but in the video, I talk about that when this cataclysmic event happened out there in space, one of the things is going to do is release G1 light. It's going to be light coming out like crazy, but at the same time, I'll say it in Dave's way, nucleons and other particles, smaller particles, emit G2 which generates a G2 wave. You get this big cluster, and a bunch of G2 particles come flying down, hits the interferometer. If it hits in the right way, it's going to change. It's going to either slow down or speed up the light wave, depending on which way it hits. And they had these interferometers all over the Earth, waiting for this to come. So, you gotta, I'm taking it from a TPM, a particle model perspective, that these G2 particles do exist, that it could have. I have no proof that it did. I have no proof of that at all. It says, though, that that's a model. You're asking for an alternate view. This is an alternate view of what happened at that event and how it would affect the interferometer. And it, according to the standard way that we have G2 particles and gravity affecting light, it can slow it down, speed it up, bend it, so it certainly could interfere with the interferometer, giving them the phase shift that happened when it happened.
So you want to hear a disagreement? I don't agree that the G2 is responsible for that, but it doesn't really matter. What matters is that we have a model and we can hack it. I mean, it was a first attempt with my dad to hack that idea. So I'm not sure. I think G2s are released maybe in a different way, but it could be right, could be wrong.
We don't know what's happening in this huge explosion.
Yeah, well, I mean, the whole thing is, if you think about LIGO, the problem with LIGO is that you have people who don't know what gravity is, who don't know what light is, claiming to say there are gravity waves, which is a wave, it's a particle, it's space-time, it's a graviton. You have light, which is a photon, but it's a wave. They have no idea what's going on. So any conclusion that they are making about LIGO is, in my opinion, is based on faith. I don't know what it's based on. So I think it's more based on being famous and trying to come up with something that sounds really great. That sort of is related to, I guess, Einstein, so they can win Nobel Prizes. And guess what they did? Kip Thorne, the only man alive today who I would say he is the only living scientist who makes a living at relativity. It's Kip Thorne from Caltech. They have zero respect for that, unfortunately, but he got one. They threw him in the mix so he could win his Nobel Prize and put it on his grave, because I'm sure he's like in his 90s now or whatever. But unfortunately, truth is not being searched out. Fame and fortune are. So, alrighty.
What is the G2? Yeah.
Yeah. Okay. Yes. Theoretical concept that light is. Yes. Theoretical concept that light from its origin source may be different than it takes from your eye back. Did you understand that? I'm not sure.
Yes. Are you saying yes?
Okay.
Quote,
Okay.
theoretical concept of light from its original source may be different than it when it until it's different when it finally hits your eye.
Yeah, and then Jerry says, that's cool. Thanks for the response. I agree much. The effects were faked. Yeah, unfortunately, when you go look at it, you get two symptoms. Either they literally fake it, or they make a stupid mistake, an assumption that's wrong, or they just simply don't have a model. So they're all guessing. We don't have an alternative like the particle model, which we do. My father and I do. So we have an answer. We have a comeback. Like, well, what do you know? How can you explain it? And I go, yeah, we can try it with our model. That's what we got. So yeah, those are sort of unfortunately. And let's see. Basically, the one-way speed of light can be measured. Can't not be measured. Oh, I gotcha. Tommy Bird, that is a great question, and I understand what you're saying. One-way speed of light. That is, let's turn on a light and measure the speed.
Oh,
it's a good question. We should be able to put.
Okay, yeah.
Or what we can do is we can go to the G2 level, the level below the G1 level, construct little mini machines that can sit on it, and then because they go really fast, then we'll be able to.
Don't believe. Don't believe.
But I think according to us in our model, we're saying that G1 particle, which is gravity and light and magnetism and electricity, it's all the same, because if they all travel in general in the speed of light, they got to be the same particle. Well, guess what? They don't always travel at the speed of light. They'll slow down at times, right? Okay, and okay, here we go. This is another one. What has been said lately about gravitons? Actually, it's
part of the standard model. Gravitons is one of the particles of the 16 particles in quantum particle theory. Gravitons are there, but they call it a mysterious particle. What I've read, and I don't study it, by the way, that carefully, but it seems like it's there because they expect that in a particle, the quantum mechanical particle model. I'm not saying this right. Gravity has to be a particle like all the other particles. They have the photon, they have the neutrino, and so for gravity they have the graviton. It's listed there. But some of these people working on quantum mechanics are actually looking at string theory as an alternate for gravity, and loop quantum theory for alternate gravity.
Shoot me now.
And I don't know how they're trying to make that mathematically compatible with all the other particles that they have, and they're not getting there. They've been trying 100 years, 80, 100 years to get that resolved. But gravitons are listed in the list of particles.
Yeah, they are. They're listed there with the I guess they call them elementary particles that don't have pieces, right? I guess that's what it is.
Yeah.
There's certain. I think electron is that way, right? Electron doesn't have any pieces.
The electrons.
Yeah. Right. So
and the positron.
Yeah. So the gravitons, I have heard about it because they are talking about this unification of general relativity and quantum mechanics. Like that's going to give them an answer. They're just so loster than lost. Okay, here's some more interesting questions. In either of your view, is gravity instantaneous? Oh, Dad, have we? Oh, well, basically, I will explain a little bit. For my dad talks about it. But my dad's a pretty good expert in this. One of the first books he stole from me, you still have it, I think. It's Pushing Gravity, right?
Yeah.
And in there they talked about
I
gravity
bought you
was
one, gave you one.
Oh, you did? It's probably over here. Yeah.
You lost it.
No. It's over here. I'm pretty sure. That's what I thought. I thought I saw it when I unpacked. But anyways, they talk about Pushing Gravity, which is an older book by a lot of people who are contemporaries before we were really working on our stuff. What was his name? Anyways, they talked about gravity is super, super fast or almost instantaneous. But the truth of the matter is, the mainstream science does agree with us, and that is gravity is at the speed of c. And there are, what, 2 experiments at least that show gravity at the speed of c?
The latest one by the Chinese is probably the best. In late 2012, they did an experiment with an eclipse. Was it an eclipse? Probably was an eclipse, but I'm a little bit muddy on that point. But they were actually measuring the gravitational delay from the moon, which is very difficult because there's only 1.25 seconds in terms of light.
Right.
And they concluded with their test that it was speed c.
Right.
But instantaneous, Newton talked about gravity, instantaneous light at a distance. But at their time, they also thought light was instantaneous.
Right.
And as long as both light and gravity are instantaneous,
they're the same.
It turns out that Newton's equation works.
Right.
Whether it's instantaneous, or both at speed c, it works, and it could even be half c. But my first clue was back in, I remember clearly, it was 2008, and I woke up in the middle of the night thinking about the Allais anomalies and the Wang eclipse, and I said to myself, wait a minute, it's not about the anomalous part, it's about the timeline. And I concluded at that point, without any other information, that the physical effect of gravity and the visual effect of gravity during an eclipse appears on the surface of the Earth at or about the same time. You can't get precisely at the same time. If you try to calculate it from those charts, I don't think you'd get the answer I'm saying. Just it got me to thinking, they're probably the same. And I stuck with that until this Chinese report. And the report came out in January in a Chinese newsletter in January of 2013. I had a copy of it one time and I read it, and they did an excellent job of the analysis, but I read it once and I can't repeat.
You gotta find it, in other words, right?
Well,
we'll have to find
it's out there. I found it in the first place.
Okay, so we're gonna have to find it in the second place because we're gonna need that for our book for sure. So hopefully that answers the question. Gravity is I guess, Jerry, the easiest way if I were to talking to people who are not like science buffs like we are, the way I would say it is like when you have the eclipse of the sun, it turns out that when you put a pendulum in its path, it goes really nuts just before and just after the full eclipse, and it turns out that the light coincides with the messing up of that is when that happens, the pendulums, so you have light and gravity coming together and having 2 points of coincidence, and because of that, then that's why we think so. What is a G2 particle? Well, it's a particle my dad didn't believe in for a whole lot until he finally said he needed it, which is right, because just because your son tells you there's a G2, it doesn't mean there is. But it all
just
comes
because you told me Einstein was wrong, I didn't believe it.
It all comes from this here. I'm going to take yours down there for a second. It comes from this, and that is, if you see the gravitic pattern here, and in our book we talk about that in the very beginning, and that is any particle that you see, anything that goes in a path that goes curved, whether it's magnetic field, whether it's an orbit, whether it's a comet, whether it's an electron around a nucleus, the reason things curve is because of a gravitic field. And so we say in any level of the universe, whether it be a cluster of galaxies that are going around other clusters of galaxies, that there are going to be a gravitic field that's responsible for that curvature or orbit. So therefore, we know that electrons go around nuclei, and when electrons go around nuclei, we say that these are the basic movements in the universe, that a gravitic field is what causes curvature. You put a mass in it, like a nucleon, you put something go past it, it will curve around. So that's the way, and that's the reason we are saying there has to be a G2 particle, because we don't believe things curve because it's cool, or because they know something, or because somebody puts a plus on something and a minus on something and say it's a field. A field of what? So that's what a G2 is. I'm not going to talk about. My dad will get into a lot more details of how we actually are using that.
What about the source?
We're not going to talk about that. We talked about that in another video. We'll be here all night talking about
Okay.
sources. Did you say that Kip Thorne does or doesn't believe in relativity? He makes a living off of it. What I'm saying, I said that out of the blue. I'm sorry, Jerry. I had my mother in the film call up. I had a list of 50 universities, and I had her call them up, and I had her tape all these conversations. We only got one person to come on to talk about relativity and take the questions that we had about relativity. Turns out that almost no one at any university says they're a specialist in relativity. In fact, the class, the advanced physics class that we filmed in the film in 2005, 2006, these advanced physics students high school, they skipped the chapter of 46 pages on relativity because the teacher says they don't like it, it's totally irrelevant. So the whole thing is relativity doesn't make anybody any money anymore, because in 2010 the rights to Einstein's image and his equations were how do you say it illegally when the rights
copyright was over?
No, it was over. There's a period of time at which it's valid, right? Well, it became invalid. That is, they couldn't use it anymore to get money, because every time you wanted to use Steven Spielberg and AI in the beginning of the 2000s, had to pay $600,000 to the Israelis because they was using his Einstein as in the future, and this kid talking to them, and because they owned that. Well, once that wasn't there, no one really is making any money. Before that, Einstein was the second largest grossing dead celebrity on planet Earth, who was making about $10 million a year. So he's making $10 million. He's not making $10 million a year. And people in high schools don't even study because the kids don't like it. It's totally irrelevant. They don't see any relevance to it at all. And people in universities also don't see it. They teach it. They all say on TV that it's the most important thing. They have to unteach it but yet it's still hanging around. Why, we don't know. So to find even not a high school teacher, but even a college professor who claims to be a specialist in relativity, that is almost non-existent. And what I was saying is that Kip Thorne is the only one left, and he must be in his 90s by now, or in his late 80s, who actually, couldn't you probably say, I make a living at relativity. It's the only person. So that was that story, long and hard, okay? Does gravity consist of particles or waves or both? Again, we'll go to this. This will answer the question for you. That's gravity, anything gravitic. Gravity is the result of particles flying in all directions. And when they are flying in all directions, that if you put something in the middle of that, it blocks out some of those things. It bounces off and it creates pressure differences between things. It's called the shadowing effect. You can look it up, Jerry. We have that in the book. It's very important in the book. It's in the very first parts of the book for the intuitions. But that's the way it is. And we say that all orbits and all curved paths are caused by gravitic fields. And if you think about it, the universe is going to be full of particles that are similar, that are going to be flying around in random directions. That's going to happen. If suns are spitting out G1s, which they are, they're blowing atoms apart, and they're what we would call electrons. Then basically what we're saying is that the gravity is caused by electrons flying in all the different directions. The only difference between our electron and the G1 particle, which is what we call it, is there's no charge. Electron with a charge on it, it's got some special property that makes it magic. So we don't have that. So that's what it is in our model. And what we're finding out is with these 4 types of movements, we can describe the entire universe. We don't have to have any special anythings. So that's the most basic field, is the gravitic field. Let's see. Okay, so it is. Okay, we answered that question. What will be the books published? What will be the books published? What will be the books publisher be? Okay, what will the books publisher be? It will be us for now, unless people go, oh my gosh, this is revolutionary, and then what normally happens, you'll be approached by something. Actually, the company I work for, which is totally different from what I do, because I work in artificial intelligence and natural language processing, getting computers to understand human language. That's my specialty, but we work for a company, LexisNexis, which is part of Elsevier, which is, I think, maybe the biggest publisher on planet Earth. But I've already asked them about them. They're very intrigued by the book, but they do not publish popular sort of science books. They publish science books that are textbooks. So we are going to be publishing it ourselves, and we hope that someone will say, oh my gosh, this is revolutionary, or this is not revolutionary. And if they do say revolutionary, someone will come to us. That's usually how those things would work. Does the moon block the sun's gravity? Absolutely. That's how gravity works. Think of the gravity as a bunch of ping pong balls being shot in space in all directions. And so they're hitting, so if you're an object in space, let's call it golf balls because that's got more momentum, right? It's a little heavier. So you've got a big ball in space. That's this big solid ball, and maybe the size of a giant ball that you can hold in your hand. And you have all these golf balls coming in all directions. It's going to pretty much stay in one place. It'll be bumped around, but it's going to stay in one place. If I bring another object, another ball the same size near it, what's going to happen is those balls are going to be blocked. Some of the balls that are hitting this one over here are going to be blocked. So the pressure in between here is going to be less, okay? And if that's the case, then they come together. It's called the shattering effect. So it's been known for hundreds of years, that concept. So this is nothing new. We just adopted it in our model in a different way, saying that at any level in the universe, we're saying that any orbit or any attraction or what looks to be gravity orbited or falling down on it, any curve is caused by a gravitic field. And we have G1 particles, we have G2 particles, and if G2 particles bend, then and going curves, there's going to be another field below that doing the same thing of field particles. And that makes sense to us because the most random, stupid field you can think of in the Newtonian world is particles flying around in straight lines all over the place. No order, zero order. So that is one of the things that can bring order to a universe. Okay, Tommy Evert, I've asked your dad before, but I'm not sure I completely understood his answer. Yeah, can you believe that? My dad thinks he's clear. He's clear as mud. I'm kidding, of course, folks. I'm just kidding. In your model, if gravity travels at c, then how does the Earth orbit the sun in its place and not where it is 8 minutes ago? Oh, Dad, this is like your...
Well, I mean, that's a valid question. This isn't an answer to your question. But if you're standing on the Earth at high noon and you see the sun straight overhead in the southern sky, being in the northern hemisphere, physically, the light you see in your eye came from that spot 8 minutes ago. And 8 minutes ago, you were in a different position 8 minutes ago, and you meet up as the Earth spins. You meet up with that image.
Right.
Okay.
Very good. I like that explanation. Wow. Very good. Keep going.
Well, and so that in a sense compensates for that delay. But the fact is, by the time, another view from the surface, if you see the sun up there and you think that's where the sun is, okay, then what you're really saying is the light from that physical sun straight overhead moved from the 93 million miles in an instant. That's instantaneous light. If you think the sun is where you see it,
right,
the light has to travel, and you can see why Newton thought that. That made sense. I mean, the only way that light could get from here to there and the sun be where you see it is if it were instantaneous, and light isn't. In fact, when I forget who measured the speed of light first, that was a big change for everybody. If gravity travels at the same speed, the biggest complaint is that the force of gravity caused by the sun on the Earth will be 8 minutes behind, and somehow the angle of the force of gravity is going to push the Earth out of orbit. It can't stay there because it's behind. So instead of hitting it directly or attracting it directly, it's going to attract it from behind and push it out or push it in. I forget which way. The solar system wouldn't work. But today, everybody, I think, inadvertently, whether they know it or not, when they take measurements of where stars are, where the sun is, where the planets are, they're assuming instantaneous light, instantaneous gravity, and they apply Newton's equation and it works. They have no problem. But if you assume they're both C, now things are not where you think they are. What you see up there isn't there; it's somewhere else. It's moved, or I'm not talking about our sun, but it's moved. And so if you try to accommodate this delay, this difference, and it's really over here, now I got to adjust something in my equations to account for the shift and the change. All of a sudden, the whole thing gets complicated.
Well, the other thing is, though, too, which is very interesting, because light and gravity arrive at the same time, you're just thinking, that is coordinated, right?
Yeah.
So that one's coordinated. So when you have the full eclipse of the sun by the moon, and you have the pendulums, at the same time you get into the full eclipse, the pendulums go wild. When you get out, they go wild, and that shows you that they're arriving at the same time, not instantaneous. There's nothing instantaneous in our model, right?
No. But it's a good question, because all of a sudden it starts getting you thinking about where do I see it and where is it and how do I compensate for that, and my guess, I'm not a cosmologist, I don't work on it every day. My guess is that everybody assumes, whether they know it or not, that light is instantaneous and gravity is instantaneous. And it works. You can calculate using Newton, or if you have to, general relativity, whatever, based on it being instantaneous. When you try to move things around because of the 8-minute delay, it's a nightmare.
Yeah. If you're then trying to go back and say, okay, this is really where it's at, yeah.
But if you do it and do it correctly, you'll find that it's going to work too.
Yeah, it will. Absolutely. He also says, I have actually been thinking, writing, and talking about relativity for over 25 years. Wow, all by himself, or maybe we have people talking about that. My gosh, the MPA was, if you watch my video today, we were known as the anti-relativity group for many years. So, plus the Big Bang, of course, many people, Borchert's the best one on the Big Bang to show you how there's all kinds of things, even philosophically, why that doesn't work. And other popular science fiction-esque ideas. Very good. I think this comment was Dave was talking about open source, meaning our book. Yeah, I've even thought about that. Once the book gets out, we have it Hack 3.0, but we're going to be probably adding to it. So it'd be 3.1, 3.2. Should we be the only authors of it? I mean, that is an interesting question, because we could not only have, we could have, I haven't thought, get this, no, this is Dave D Hill, sir. This is my idea here. Open source model of the universe.
Very good question, but I'll tell you in what area I would work. And in fact, I've said this on when I talked my videos on my experiments, my resistor experiments. I suggested you can do this experiment too, and if you do the experiment and you get the results, I'll work with you to see what your results, and we'll try to figure out whether the prediction the particle model makes about the circuit is valid or not. That circuit, I got it all set up in my office over here. I got a lab in my room.
He's trying to get people to do it. I'll tell you, it will happen.
No, but what that would be great to have an independent person All you need is a power supply, an accurate voltmeter, and a bunch of resistors.
Can we?
That's all.
I don't want to throw water on this, but let me ask one question. How much is the accurate voltmeter?
Brand new,
Yeah.
$5,000.
There you go, folks. There you go.
I got a used
People are like-
one from Keysight for $2,000.
Yeah, I helped them with
I paid
that.
$2,000.
I know how to buy stuff real cheap, folks. Okay.
But I would, and I'd be willing to co-author a paper, and
I've already
maybe
co-
it eventually gets in the book.
I already co-authored, and people will do that, Dad. It's going to happen. If this stuff is right, it's going to happen. So.
I'm promoting the idea. That's all.
Okay. I didn't realize gravity is a possible way to block. Of course, light gravity, though, that's wild. No, yeah. But again, Jerry, that's been around for hundreds of years, that idea. It's called the shadowing effect.
It was 1748 that Lesage published his first idea about this gravity.
Right.
Newton knew about it because his friend Nicholas Fadio told Newton about it. Newton was going to put it in his book, and he backed out.
Right, yeah. He wasn't too convinced yet of that idea. How is the velocity of gravity shown as accurate? How to know for sure that gravity is or isn't instantaneous? Well, again, that we've talked about that basically with experiments, the Allais anomaly. How could gravity be at instantaneous if your pendulums go nuts at only 2 points, which happen to exactly coincide with the beginning and end of the total eclipse, which we have some explanations for because gravity does travel. So, and the other thing is too, Jerry, we do not believe there's any instantaneous anything in the universe. So
Newton didn't believe it.
Yeah, Newton didn't either. So we believe in the
Does
Newtonian world.
relativity believe that gravity is instantaneous? Those gravity waves probably, I don't know what their estimate was about how long it took.
Gravity waves are different than gravity. So
Yeah, I get it.
And let me say, gravity waves, which are invented and we don't know what they really mean, are different from gravity, their gravity, which they don't know what it is
And
either.
we don't have gravity
So
waves.
it's, you're talking about two fantasy things. I don't even know how to say to answer that question because they don't have a model for it. So don't even bother trying to wrap your head around that. Okay, why wouldn't the sun that vanishes in the sky, that both the light and heat immediately disappear? It would not. Absolutely would not. Well, we know that light takes so much time to travel. I mean, we send light signals or signals with G1 particles to communicate, and they take so much time. What, 1/4 of a second from the sun or from the moon, right? So that's
1.25 seconds from the moon.
1.25
8
seconds.
minutes. It would appear to take 8 minutes, but
From the sun.
I think there would be a lot of other terrible things going on at the time if the sun disappeared. By the way.
Yeah, that would be good. But it would take us 8 minutes to feel it for sure. But it would wreak havoc for sure. Let's see. Here's a person that says, I do like the explanation of perspective due to motion. It really does make sense looking at it that way. And I never had it explained in that matter, period. That's exactly what I thought you guys. Yeah. You know what's really funny? And this is a really, really something I've talked with my dad several times. It's really worth talking about. Is that it's a couple of things. Even before we had the model, we had enough I had enough explanations from other people's work outside the mainstream that every time I talked to any friends about science, they were really they would ask me every time I meet people. Shane, right? A guy who's a friend, who's a social acquaintance through my wife, who's a Brazilian. Every time we see him, oh, you're the science guy. He comes up, is it true that snakes used to have legs? Or I don't know. I'm just kidding you. But the thing is that we give answers according to what we think is true, not with what we think we know and what you don't know, and therefore we're going to tell you what we don't. There's no ego involved. And now that my dad and I have a particle model, we can now answer questions that other people can't answer. I'll give you a good example. If you go back to one of the videos that we did in this series right now, we talk about the bucket, right? Newton's bucket, and how when you spin a bucket of water, you get a concave surface. Well, the explanation, Andrea Cis, who's a really great Brazilian, he's a person that works outside, who works in the dissident area. He works he's a physicist in Brazil, and he is works with Weber. I think he's a Weberian. I think I won't talk about that. But anyways, he talked about, well, it must be that all the galaxies out there tell people up, here's the water, and this causes the this concave because there's all these objects out. And when I looked at it, I thought to myself, why is he saying this? Well, because he really doesn't have a model for gravity, he doesn't have a model for light, he doesn't have a model for the atoms and how they interact and all that kind of stuff. And so when you're trying to do explanations, you're stuck with the equations. And the equations talk about, what was it, torque? No, it was not torque. A rotational...
The angular momentum.
Angular momentum. So he's talking about in his book, Relational Mechanics, which is his try to add a model for the universe. Well, he talks about the rotational
universe.
Angular.
No, there's angular velocity, and along with mass and angular velocity, you have angular momentum.
Right, angular momentum. So they are stuck on that one little variable in their equation, and then they talk about that as if they translate to a physical world. What they are not doing is saying that this is the way the world works. These are the physical parts of it. We have that. So the reason my father and I, when we answer questions, are more confident is because we're basing it on a model, right or wrong. At least we're basing it on a model. So when we talk about it, we are talking about it with our feet on a model that has, real foundations, real foundations. And because of that, we can tell you that, in fact, the Newton's bucket has nothing to do with those things out there, except for that there's a gravitational field, right? It's just Newtonian, and you can explain it. There's a gravitational field, Newtonian. You can do this in space, and what I claim is the water will stick to the edges. Because water, when it's on the bucket, you're pushing it this way. The water wants to go with the side of the bucket, so you're literally pushing water molecules in a straight line. But then there's a bucket in the way, and it bounces off that into a straight line, bounces off, and it's just all the forces, etc. So yes, it's very interesting that my dad and I, especially my dad, has a lot of great explanations for things because we're sitting on a model where we don't have to worry about, are we an equation? Because we don't have equations. We don't have equations telling us, well, the gravitational equation says the 2 mass and the g, and therefore when this thing happens, then this is just changing this and the radius. No, we have a model. And I think that's one of the reasons a lot of my father's especially, and even mine, a lot of times people find these our answers satisfying. Let's see. What's it say? He's saying, what about the pendulum again? Though it goes crazy during eclipse or shortly after. It basically goes right when the right when the eclipse happens. When the eclipse goes to that diamond ring, right before it goes from it's not
right
full.
At the center. It happens before that.
Right.
It happens at the first touch of the eclipse. Something happens right in the middle sometimes.
Right.
And it happens at the tail end.
Right.
There's a gravitational bending going on that modifies the gravitational field towards the pendulum and will knock it one way or the other. What people observe is this. When you stand watching a pendulum, it moves clockwise because the earth below is moving counterclockwise. So you're standing there, you're moving with the earth, and it looks like the pendulum's moving clockwise. During the eclipse, the first touch of the moon visually, the moon with the sun, this son of a gun jumps backwards. And then it wiggles around and it jumps, and then somewhere later it starts coming back. But when it's all over, this is the odd part. The graphs of this records of this. It's got a normal line that they expect it to go, and it's going clockwise. It jumps back counterclockwise. It goes all over, and by the time it's all done, it's right back where it's supposed to be. Maybe not
right.
Exactly.
That's bizarre.
It's bizarre. So things. It just it just jumps. And Alade did one experiment in June of 1954, recorded it, and another one in October of 59 and recorded it. And people look at these motions and they say, it's crazy, it can't happen. They call them an anomaly. And most people walk away from it and say, I'm not going to explain an anomaly. Well, we're dumb enough to try.
No, we have a model, so
Yeah,
we should
so
be
we
able
have-
to. We should be able to explain it.
You have another one in 1997 in China done by a group of Xian Chen Wang. He had a group go out and use a gravimeter measurement. He found two bumps right at the beginning and right at the end. And there was a unexpected deviation in the middle called an anomaly. I have videos on anomalies where I talk about these issues.
Subscribe to his channel. He talks about
It's very interesting to think about it. Maybe my explanations aren't quite right, but at least it's a start.
It's a start, right?
To truly understand it, and we're using the particle model idea that there's the G1 gravity field, G1 light can bend, G1 gravity can bend. It's the same particle. It's got if
And the
if that's
bending
right.
happens within. There's things in space. Nothing's going to bend in space if there's not something there. It's not like space-time.
Right.
Space-time, which is
It's the
nothing.
sun and the
It's-
moon.
there's a corona, and the corona has stuff in it. And anytime you have really mass or stuff in it, things can bend, just like water will bend light. What we say, water doesn't really. Well, uh, long story, but yeah, we can explain that with our model. Okay, let's go forward because we got. Oh my gosh, we've been going an hour and a half here. To extend from a previous question I asked, what alternative views exist that account for some of the alleged proofs of relativity? The muons and the oh yeah, we know all about this. I will refer you to a website that's down, Autodynamics. That's my mentor Karazani talks about the muon. It's in autodynamics.org and it's down. I've got to find it because we've had people hack it for many years. People have been perturbing us. We've had trolls for many years before trolls were even named trolls. So yeah, muons can be explained without special relativity. That's supposedly it should happen slower, but or faster, the decay of the muon. And they said, oh, it's going faster or slower than it should, therefore it's special relativity. And then they say that. Why particles in accelerators can't reach C because they're using gravitic fields. Magnetic fields. To do that, magnetic fields are G1 particles. G1 particles go at the speed of C. They don't go faster than the speed of C. They may go a little faster, but not enough to make a difference. So that answers that question.
Well, there's a lot of things there, Jerry, that'd be a long time discussing.
No, we can answer them quickly. My dad will take longer, but we're
What-
going to answer it quickly. Why do particles can't reach speeds? Because the things that makes the things accelerators is like if you're on a bicycle, right? And you're stopped. The first person pushes you on the bicycle, you start going faster. They go as fast as they're pushed. Then the next person, if they can push faster, they can go faster. But eventually you're going to get to the fastest speed anybody can push. You're never going to go faster than that. And what we're saying is that G1 particles are going at the speed of C. You're using magnetic fields, which are G1 particles, to accelerate it. So you're not going to go faster than the accelerant, which is C.
Well, that's the forcing issue. But most often, for example, they don't, I don't know, they accelerate electrons?
No.
They accelerate protons?
Yes.
Now, proton is subject to G1 gravity. Okay?
Right, but here's well, we got a lot of questions to answer.
No,
Okay.
yeah, that's why I say, go ahead.
Yeah. I think what's going to happen, we're going to get into a deep explanation. What we want to do is probably try to get these a little quicker. We can go into deeper questions maybe later. Why objects everywhere can't reach C? Well, that's the objects in our level of the universe. Their G2s are traveling faster than C. And there's our model should open up the idea of, well, if we can get down to that level, can we then? The question is, since let's say a spaceship and ourselves are made out of a nucleon with G1 particle going around and it's going at speed. If we go faster than, really, really fast, are we going to tear apart the atoms? And can we shield that from being torn apart? Well, and we can't accelerate ourselves faster. We'd have to somehow use G2 particles to accelerate G1 particles or nucleons, which may in fact be an impossibility. But maybe.
But atoms, molecules will be slowed down by a drag caused by the G1 particle field.
What G1 particle field?
If it's stopped, you got G1 particles hitting an atom or a molecule from all sides. It's stopped. There's no problem. You go close to the speed of light. The ones trying to push it as fast can't get there to push. The ones coming this way got a double force pushing back.
Right. That's what he's talking about, like the bicycle problem. But one of the things is, and this is just something that's very interesting too, is that the speed of light is something people have dreamed of to go faster because they know it's really fast. Unfortunately, because we didn't have a model for anything, we just assume that that's going to happen. It's just going to happen that we're going to be able to do this. Now, if you think about it, and I'm thinking right off the top of my head, literally right off the top of my head, if you think about it, it would be the same as saying, I've got a 2x4, and why can't I have this 2x4? I can put the weight of a whole skyscraper on it, or a giant airplane on the 2x4, and why would it break? I want that not to break. What you're trying to do is you're saying to someone saying, I want to go faster than the speed of light without having any knowledge of the physics behind what that would be. You're just saying that, why is it a limit? It can't be a limit. Well, why is it? Do we have other limits? You can't. Literally, there's a physical world. There are things that work in the physical world. There are reasons behind it. There's a model behind it. With that model, you should be able to say things. So, it's just an absurd obsession we have that say we've got to go faster than speed of light so we can get to places. Now, our model does give hope for that because we know there are things that go faster than speed of light. For instance, one of the things that I've even talked about, one of the people who know about our model saying, why don't we look into G2 particles? Can we control those? Because we could communicate to Mars in a fourth of a second with a G2 particle, if we think that's how fast it's going for real. So the idea of going faster than the speed of light is like saying, why can't my car hold all the weight of all this of my entire house and I can drive it? Well, there's limits to the way the physics of the world works. You can't just wish upon something to happen. So maybe that is a strange way of answering it, but I think that's let's see what else you have here. Why objects can receive the time dilation with gravity. Time dilation it doesn't make any sense because time, I believe Borchert says it's movement. We use time to measure movement. So this whole idea of time dilation or time slowing down or going backwards, movement is movement. Movement doesn't have a direction. Doesn't have, time is like going backwards. It's movement goes, and that's the direction you have. There's no negatives in the universe, so going backwards. Hey, that's it. Wow. We just answered that with a particle model somewhat, with a non-negative in the universe. The reason you can't go backwards in time is there's no negatives in the universe.
Yeah, but time is a man-made concept to measure motion, and there's nothing real about time. We're the ones.
Well, I know, but
set it up.
Yeah, I know, but I'm just saying the reason that you don't have time going backwards is because there's no negatives. That's the answer.
Well, in
I'm
a
writing
way,
this down. I'm
saying
making a
the
video.
same thing. You're
I
saying
said
it different.
first.
You're saying
I'm kidding, Dad.
the next event is always time stamped with a positive addition, not a negative addition.
Right,
You don't time stamp
But I'm just
tomorrow as the day before.
Now
You
you're
time
saying it
stamp
because
the
I
next.
said it. So that's
That's
cool.
not negative.
Right. So I came up with something cool right tonight. I wrote that one down. That's a big one. Time dilation about shifting starlight during the eclipse.
Yes. Yes.
Yes, it happens through the corona. That is, there has to be something. If you're outside the corona, if there's nothing in space, Einstein says it still should curve. It doesn't curve. He's wrong. End of story, that one. How relativity accounts for Mercury's irregular orbit. Oh, that's a long one. We're not going to go into that one. Long story. We can talk about that all night. Yep, you're asking every question under the sun. Uh, uh, Here's one. Could the word model serve as a synonym from premise or axiom? No. I'm a linguist. I'm not saying that give the definitive answers, but I worked 35 years of my life trying to get meaning out of words, what we use, why we have words. The reason we have words is they have to have some relationship to the real world. Model means a mechanical model is the way I see it. When you say if you have a model to someone, they're going to say, show it to me, put it in my hand, make a 3D of it, put it here. If you can't do that, in my opinion, it's not a model. So a premise and an axiom is not that.
See, our model isn't a real thing.
An eclipse takes quite a while to completely happen, though. Yep, it takes some time to say. Okay. If it happens in the first touch, why does that mean that gravity is instantaneous, though? Because it's the light we see. This is an easy answer, Jerry. The light we see and the gravity coincide. So it looks like they're coming at the same time, but it's not instant. Because what you're saying, Jerry, would be is that what we see where the sun is exactly where the sun is. It's not where it is. It just happens that where we see the sun and when gravity comes happens to be coincide. And that's a nice coincidence, but it's not. That's sort of the way the universe would work. Is it possible to code gravity into a 3D computer model and make it like code like? Absolutely. In fact, our whole model could be verified and find out exactly how this all could work by using a 3D computer model with the simple gravity equation in there. And yes, our entire model of the universe should be able to do in a 3D collision model. That should work.
Excuse me. Very first thing I did when David asked me to do the experiment was I generated a gravity equation using the particle model. We didn't call it back at that time. My final equation was a double summation. So it took me 10 years, but I got a calculation done using a double summation, which in effect is a 3D analysis of an experiment done by Majorana in Italy in the 1920s. I modeled his experiment using his results. I've got values for the constants of my equation, but that equation was a two summation. Select a plane, select an angle in the plane, and I calculated three-dimensionally the forces of the Earth in a lead cube and a lead ball.
Gravitational field is not a sphere unless you have a spherical object that's that from a point is the same density from that one point in any direction. That's the reason people postulated dark matter. That's why if you watch my video on dark matter, you will find out that the two galaxies they find out that don't have dark matter are spherical galaxies because there's no funny things going on. Galaxies do not have spherical gravitational fields, and it makes sense because if you go way above of one, you're not going to curve very much. But if you go right next to the edge, you're going to curve because you're going to be closer to stars. This is the reason why. And this is why they postulated stupidly that kind of. Oh, look at this! He could talk to us all day, and my dad could give you answers all day. But let's see where we are now. Let me see here. Why does drag occur coincidentally at C? Why does the drag occur coincidentally at C? No, C comes from the instantaneous impact of a G2 particle hitting a G1 particle, and that momentum is around C on the average, right? So basically,
well, there's G1 drag and there's G2 drag.
Right, but
G1 drag.
He's talking about C. C is the speed of G1. Let's keep it. I mean,
Okay,
you're going to all the levels.
I'm just trying to clarify. So
they're trying to add
drag,
stuff to it.
Now, drag by the G1 particle, which is moving at C, tends to.
That's not what he's asking. Okay, let me ask. Look at this question. He's saying drag occur coincidentally at C. What he means is there's something traveling at the C, and what's the drag on that? Okay, that's what he's asking.
Is that what you're asking?
No, it just says, why does the drag occur coincide at C? C has to do with G1 particle, not G2 particles, but that's what he's saying is the drag on C. C is G1 particles. So if he's saying what's
I
drag
don't-
on C, he's saying what's a drag on
Sorry, I
G2
don't read
particles.
it that way, but maybe you could restate the question, Jerry.
No, that's what he's saying.
Okay, you answer it. Go
Okay.
ahead.
Do G2 particles travel at C?
No, you're asking
No,
a
no, I'm
question.
not-
Just
no,
answer,
but I'm
answer
saying-
his question.
Right. What I'm saying is it coincidentally at C. So if the moment you mention C and drag, what I'm saying is
So why
what's
does it?
traveling is G.
Why?
Because
That's
G1 particles are traveling at C is because you have G2 particles hitting them. The reason they'll have drag is because you're hitting with G2 particles. So that answers them. That's all right. We don't want to get bogged down in the stuff. So you mentioned of how a friend who has multiple patents in GPS. I've heard countless times GPS has proved general relativity. I've heard countless times GPS. Yes, of course it does. Yeah, that's what they say. And if you get the quote from my film, I'll give you the quote, and it's actually in several of my videos, which I get right from my film. He says, GPS does not support relativity. It actually shows the flaws in relativity, and that's what he says. Both in special and general, not one or the other. The reason clocks slow down is because the gravitational field is less. And as much as we want to say a atomic clock isn't a mechanical clock, yes it is. Isn't that right, Dad? An
Yes.
atomic clock is a mechanical clock too. So if you put a pendulum in space that relies on the gravitational field to make it go back and forth because of the particle, the G1s are pushing it down, you go out into space, good luck on trying to get a pendulum working in space. So it's the same thing that happens when you take clocks. They have to adjust them to the microgravity up there. So let's see, does G2 particle, oh wait a minute, here's another one. Does the G2 particle actually have mass on our level of the universe? Very good question. Is that a great question? Tommy
Yes,
Bird,
yes.
you get a free whatever. We don't have free anything right now. But my goodness, Tommy, that is the great... I will answer because my dad will go into a long answer. But the short answer is that you cannot measure everything in kilograms or pounds in multi-levels of the universe. You're not going to measure the mass of a G2 particle using a G1 gravitational field. It doesn't work. So the idea of, first of all, you have to agree that there are infinite levels of the universe, that there are bigger and bigger particles of bigger and bigger particles, and smaller and smaller particles. Once you get that, my dad is very good about doing very detailed talk about this. But basically, I think you have a video on this, don't you?
Well,
Got a couple videos.
yeah,
Subscribe
I have
to it.
videos on.
Search
well,
on
the
his.
one I have a video on the mass of the electron, and I summarized that they're measuring the mass of the electron correctly, but they correlate it to the equation of energy equals force times distance. Or no, it's a different energy. No, it's energy equals mass times acceleration.
Mm-hmm.
And they're equating two energies. The energy at level 1 they claim is the same, has the same meaning as energy at level 2, and that can't possibly be because they're both going at different speeds. They have mass. G1 has, an atom has kilogram mass or gram mass. Atoms, molecules, and larger can be measured with G1 gravity. But G2, the G1, the electron, you're using G1 particle G1 fields to try to measure G1 particle. It's not going to act gravitationally. It's going to collide, and
Right.
that's not a gravity function. Gravity requires that the gravity particle pass through the atom, pass through the molecule, pass through larger objects. It can't pass through a G itself. So it just collides. And it's only when a particle can pass through. The G2 can pass through the G1 because it's much smaller and much faster, just like the G1 is much smaller and faster than the atom. And so we don't,
You can't.
Atoms and molecules and larger can have kilogram as a measurement for mass because there's a standard.
Tommy, let me explain it sort of in more layman's terms here. When we measure mass, we use a gravitational field of G1 particles. We use gravity. Gravity, because we have a model, we know what that is a G1 a gravitational field. A G1 gravitational field cannot measure the gravity or does not push G2s because G2s go right, that's what my dad was saying, goes right through them. So what happens is when you get down a level in the universe, if you want to measure a G1 particle, you're going to have to measure it in a G2 field and give it another name, like a de Hilster instead of a Newton. And my dad says, don't do that, that's pretentious. Well, I'm not doing it because I didn't come up with the luminic stuff, but I'll name it after my father, then it doesn't sound like I'm naming it after me. So what we would say is that the G2 particle would be measured in Hilsters. We just made that up. I made that up a couple of years ago.
You've done it now.
So you can write that down, folks. Yeah, it's a Hilster. So there you go. That'll answer that.
I'm going to change my name.
I changed it. It's a Hilster, not a D Hilster. Not from Hilster. So we're from Hilster, not Hilster. Okay. Let's see. I'm just looking at these things. There's a particle accelerator. Some of these are just comments on things we talked about. Sorry, Dave. Apologize for being here. But you check another books. This is what he says. Sorry, Dave. I apologize for keeping you. On the plus, I do believe you can check another box for your book sales. I like Tommy. Tommy, I like your attitude. So, wait. We've got. You know what we should do, Dad? You know what I'm going to do is I'm going to put a little whiteboard here, and we're going to check off how many books we sold. We're almost up to 10. Almost guaranteed. My wife won't even buy one. So there you go. That's funny, though. I like your sense of humor. Like I said, we're either going down in history or going down in flames, I tell you. Don't know. Pendulums in space, similar to on-timers work. I think you just said that. Yeah. Okay. Or flying a plane into one of the synchronous clocks. That's a common clock that describes the one on the ground. Yes, absolutely. That's true. It's not time dilation or time going backwards. But today, there's no negative anything in the universe. That's going to be a whole video. That's like a whole thing. One of the things from our there's all kinds of little things from you know what? We got to get sayings or one of those little things. Like my father's instantaneous gravitational, what is it you call it?
Action at a distance?
No, the one where you have a G1 hitting the nucleus. It's a instantaneous force of gravity.
There's each particle.
It's not instantaneous.
Instantaneous force.
Or finite?
It's in a very tiny force. A G1 particle hits the nucleus of an atom or a particle. It applies a force. And in my equation, I have a term that is F sub 1 for the G1 instantaneous force of a particle, which I'm trying to calculate.
And one of the things my dad says that's really cool, like little sayings from our stuff, and he's right. There are no two collisions that happen simultaneously. There's always, if you take time and go down in the movement, get close enough to measure that movement, there'll never be two particles in the universe that ever collide at the same time. That is unbelievable. That's really cool. But of course, I won't even talk about something I would open my mouth and get into trouble saying. Let's see, because of the moments of acceleration and deceleration, at the constant velocity, the clocks remain in sync. At least I have are nucleons made of G1 particles? Good question, Farouk. No, not at all. And
too bad.
No. In fact, they hit nucleons, but what happens is, just think of it as this. If you want to use the standard model, you can say there's the nucleus and you have electrons going around it. Well, the nucleus is not made of electrons. The nucleus is probably made up of G2 particles or G2 atoms that are made with G2 particles if you want to just keep going down. But we don't know that. We would call that Hack 4. But we would say that since a nucleon is most likely circular or spherical, anything spherical has to be made out of some type of atoms or parts. Atoms are made out of nuclei and
Okay.
orbits. So we would say that the nucleon would be made out of N2 nucleons and nucleon twos, N2s. See, a nucleon, we call it N1. So N1s are made out of G2s and N2s.
Okay, excuse me. You disagree with me before. I'm going to disagree with you now. If you have two G1 particles going through space and there's G2 gravity field around it, they will get pushed together and clump as two G1s stuck together.
Sure.
And if you do enough of those, you could theoretically
Make
generate a nucleon.
a neutron star. But I don't think it's a nucleon, Dad. What I think
Well,
it is,
I just said you could.
what I think that would be, and we're just off in speculation land.
Right,
but
that's right.
I'm saying that could be a black hole.
What could be a black hole? A nucleon?
No, only nucleons or only G1 particles. Maybe G1 particles won't do it. Maybe it's nucleons. What I'm saying is the weird objects in the universe that are super dense, like black holes that don't have any G1s coming out in
wasn't
waves.
even talking about black
I
holes.
know, but what I'm saying though to you is the idea of G1s coming together and sticking together, or nucleons with sticking together without any G1s. Yeah, I mean those are what I would say are exotic things. So that's what I would say. But it's a good question, and we have the model, but we thought about it, but we don't have necessarily all the answer. It says, I have no money, I am dyslexic, books are wasted on me. Well, we can have an audio book, you can get that, so no problem. What is your view on simultaneous events?
I don't have-
Waste of time. Don't waste your time on that. You know how you have these three prongs where basically I had an architecture teacher and I answered the question right. I have my bachelor's degree in architecture and mathematics. And so he held up this one guy who thought he was really brilliant and that no one would get. He goes, how many things are I'm holding up here? And I said two. And he goes, oh, I said what? I said two spaces between your fingers. And he goes, yeah. Well, the same thing where you see is this two or is this three? Well, it's the same thing. Simultaneity of events. This is all getting into, observer and when things really happen. All we can say in our model, right? And you've said this, Dad, is
I
that.
haven't addressed that point.
Well, no, you have some. Yes, you have not this specific thing, but we've talked about this idea. And the answer to the question, which my dad has actually told me, is that observation is always going to see things where things aren't because they have moved. There are no infinitely fast anythings. So everything that we are going to observe is always going to be
Somewhere
after the
else.
fact, somewhere else.
Even what I see of David,
Yeah.
as infinitesimal
So,
as that
see?
difference is. But I didn't call it simultaneity.
I'm subscribed to particle. Don't think I could follow the constant and far, but be vague. Okay, I'm not good. You're not a physicist. You have hope. Let's see. He says, I'm a fan of both science and common sense. I wish more people would have. Absolutely. Tommy, that's absolutely. And that's what in the first part of our book, we literally show you how our model is based on common sense. And I actually draw a diagram, and with that common sense, you can use our model to hack anything that you see in physics. And anybody can do it. So I think it's time we should hit the road here. It's almost 2 hours, and we actually answer questions for you people, but we do want to thank you so much. I do want to remind you, go to our website if you want to learn a little bit about it. If you want to subscribe to us, go to YouTube, Principia Mathematica 2. That's different from my channel and my dad's channel because it's specifically about the book and the model specifically. You can go to Facebook Principia 2 because we do have 5 seeing people. We have a group of people on YouTube and a group of people on Facebook. We have the counts. We can watch their people. And so I want to thank everybody from both of those. Also, we have my dad's channel. You can get to at youtube.particle.guru, youtube.particle.guru, or look up Particle Guru in the YouTube channels. And also you can go to Dissident Science. You can find me. just put out a new video, and that's pretty much it. So I want to thank everyone for participating greatly, and was really great. It just, I think we moved it to later, and I'm thinking that's why people were able
Except
more
the
to
one
come.
guy at 2 a.m.
Except the guy in 2 a.m. who would stick around for that. But
Hopefully he'll watch it later and heard
yeah.
all that.
But anyways, I want to thank everybody, and we'll be back tomorrow. I'm working on electronic components tomorrow. But
I'm working on a transistor.
transistor. And he says, "No one wants to know about that." Yeah,
I haven't figured it out yet.
Oh, see, we're still hacking the universe.
I didn't explain it right in my video, guys. I apologize. I just used the standard explanation.
It's over, guys. My dad's explanation, which wasn't quite right, the entire model's now falsified, and it's not worth anybody's. So please, if
What
this
I
you
said
thought
isn't
was
wrong, I
interesting,
just didn't
it's
explain
not
it.
interesting anymore. You can tear it down. It's a house of cards. Not. So don't worry about the drama over
I
here.
didn't say anything wrong. I just didn't give the answer I should have given.
Anyways, I am David D. Hilster, and this is Bob D. Hilster, my dad. Say goodnight, Dad.
Good night, Dad.
Ciao for now, folks. Thanks so much.